lectures we had discussed about deriving entropy from the explicit calculation of microstates. So let us go back to our ideal gas equation, which we had written as S is a function of NVE, which is equal to K or KB ln gamma, where K is the Boltzmann's constant, such that it is given by Nk ln V by H cube 4 pi me by 3n raised to 3 by 2 plus 3 by 2 Nk. Now here we can rewrite this expression. And substitute for E is equal to 3 by 2 Nk, which we have done in the previous lecture. So E is equal to 3 by 2 Nkt. Substituting E is equal to 3 by 2 Nkt and separating V from this equation, we rewrite this equation as Nkv plus 3 by 2 Nk. This is, take this 3 by 2. So it will be 1 plus ln. Insert this inside the this 4 pi me. So first of all, by 3 when you take E is equal to 3 by 2 Nkt, Nn cancels, 3 cancels, it becomes 2 pi. So 2 pi Mkt by H square. So this is our new expression. We have rewritten our S is equal to K ln gamma expression as in this form. Now here the entropy of an ideal gas, which we have written here, this is the ideal gas expression, is not an extensive property. Whereas in the beginning itself we had said that entropy is an extensive property when we had said S is equal to Kb ln omega, where omega is, if omega is omega 1 into omega 2, then you can write it. But here you will notice that we are saying it is not a extensive property. Why? Let us say if you increase the factor by a factor alpha, and the whole thing doesn't come out to be S prime doesn't come out to be alpha. Let us see how we are going to show that. See, if entropy increases by a factor alpha, then it should be N goes as alpha, and V goes as alpha V, and E goes as alpha E, such that the whole thing S prime, the new entropy, should be equal to alpha S. Whereas it doesn't happen. Suppose if you are substituting alpha here, substituting alpha for N and alpha for V, then what do you get? You get an expression S prime as alpha Nk ln alpha V plus 3 by 2 alpha Nk 1 plus ln 2 pi Mkt by S square. This factor doesn't change. When you take alpha N here, alpha N, okay. But if this S prime is not equal to alpha S, you will realize rest of things are fine when you're just multiplying alpha externally. So you are getting actually alpha S. But in this case, you are not getting, this is not alpha S. Because you are earlier you had ln V, now you are having alpha LV. So for that, we will say S prime is not equal to alpha S. So this is a slightly unphysical situation because entropy is supposed to be extensive in nature. So there is some corrections which are needed. So this situation was visualized by Gibbs, and he considered this situation as an enclosure having two ideal gases separated by a partition. Gas 1 having parameters like N1, V1, T, and gas 2 having parameters N2, V2, T. Again, this situation, we have two gases in an enclosure, two different gases. So the entropy collectively we can write down. Entropy in general is given as SI, where I can be 1 or 2. S1 for the first case, S2 for the second case. This Nik ln Vi plus 3 by 2 Nik 1 plus ln 2 pi Mi Kt by H square. Now what we do is we add both gases. When you add both gases, the S total will be summation of I is equal to 1 to 2 Nik ln V plus 3 by 2 Nik plus 1 plus ln 2 pi Mi Kt by H square. Now V is what? V is V1 plus V2. We know the net increase in the value of S is given by, the net increase in the value of S will be given by delta S is equal to St minus Si, that is the individual atom. So here St is this one, and Si is this. So we will, what you will do is, you will subtract St minus Si, keep I as 1 and 2. So what will happen? The second term vanishes. See, the second term will easily go off for both cases. Whereas the first term, there is a difference. First term, see, here it is ln v1, there it will be ln v2, and here it is ln v. So v1 plus v is v1 plus v2. So v1 plus v2 minus ln v1 minus ln v2. So this comes out to be k n1 ln v1 plus v2 minus v1. So just v1 by v2 by v1 plus n2 ln v1 plus v2 by v2. So this expression you will get finally, which is a change in entropy. And change in entropy here is assumed to be positive. This also looks positive because it's an irreversible process which we know. We are mixing two gases. You cannot separate them again because they are two different gases. So here what happens? Entropy is given by this expression. Again, if the gases are having same number density is given by n1 by v1 is equal to n2 by v2. So n1 plus n2, that's total, is equal to v1 by v2. So here v1 by v2 by v1 can be written as n1 by n2 plus by n1. So again, in terms of number density, we write k is equal to n1 ln where n1 plus n2 by n1 plus n2 ln n1 plus n2 by n2. This is again positive. So for different gases, this is a very good, this is a very good answer, let us say, and this is valid also. Then what is the paradoxical situation? The paradoxical situation is for different gases, when you mix, entropy is increased, that's fine. But what about when same gases are mixed? See, when same gases are mixed, again the S total comes out to be nk ln v plus 3 by 2 1 plus ln 2 pi m. So earlier it was m1 plus m2, now it is m. The 2 pi m kt h square, because both gases are same. So here also when you mix the two samples of the same gas, you will get this expression as entropy and delta is greater than 0. This is not done because when you are mixing two samples of the same gas, it is a reversible process. You can always revert it back. You can always bring the partition and you can make it like before. So it's a reversible process and entropy is supposed to be 0. Whereas when we see, this expression holds good even for this case also, where the ST total is like this, where you are mixing same gas. So so this is the paradoxical situation, which is known as the Gibbs paradox. Here what is there? The entropy change is same for different gases mixing and same gas mixing, which should not be there. So what is the summary? So Gibbs paradox, actually it involves the contrast between mixing two quantities of ideal gas of different kind and of mixing two quantities of same gas. Actually both should give different results. In case of different gases, delta is greater than 0, irreversible process, it is fine, it is correct. But in the case of same gas, it is seen that delta is still greater than 0, which is a paradox. So that is not correct. That should be 0. So that is the Gibbs paradox. So now once we have learned the Gibbs paradox, in the coming classes we will learn how to solve or how to get a solution for the Gibbs paradox. So that's it. Thank you.